Maxwell-Boltzmann Statistics is a mathematical framework to describe the distribution of particles over various energy states in a thermal system. Yes, we are talking about thermal system. But there are few assumptions which must be strictly followed if we want to use this theory, that is Maxwell-Boltzmann Statistics. Okay, so what are those assumptions? So let us first discuss those assumptions. First assumption is the particles of the system must be distinguishable. That means each particle should be tracked and identified separately. If this condition is not followed, then in that case you cannot use Maxwell-Boltzmann statistics for the given system. Next point is classical mechanics. That means all the particles of the system should follow the principle of classical mechanics, that is Newtonian mechanics. Okay, Newtonian mechanics must be followed by all the particles of the system. Then in that case you can use Maxwell-Boltzmann statistics. More assumptions are there. The system should be non-quantum in nature. That means what? That means quantum effects are negligibly small in your given system. Quantum effects are always present in any system. But if quantum effects are very small as compared to the other effects, in that case these small quantities, that is I am talking about the quantum effects, can be neglected at ease, and in such a case Maxwell-Boltzmann statistics can be used. The temperature should be high of the system. Okay, if the temperature is high, then Maxwell-Boltzmann statistics can be used. If the density is low, density of the particles in your given system is low, in that case Maxwell-Boltzmann statistics can be used. So these are the assumptions. Okay, if temperature is low, in that case you cannot use Maxwell-Boltzmann statistics. In case where densities are very high, in that case also you cannot use Maxwell-Boltzmann statistics. In case of high pressures, in that case also you cannot use Maxwell-Boltzmann statistics. The last point is the system should be thermally stable. That means the macroscopic properties of the system, that is pressure, volume, temperature, these are macroscopic properties of the system. The macroscopic properties of the system must be stable. That means those macroscopic properties should not change over time. Means macroscopic properties must be time independent. So if all these assumptions or if all these conditions are strictly followed, then you can easily use Maxwell-Boltzmann statistics for mathematical purpose or for mathematical description or to study a system. Okay, otherwise you cannot use. And yes, this statistics, that is Maxwell-Boltzmann statistics, gives you highly accurate results if all the conditions are followed strictly. Here what is done? A graph is plotted, x-axis versus y-axis. X-axis represents speed, y-axis, that is the vertical one, that represents the probability density or the fraction of the number of particles. That is being represented by the y-axis, that is by the vertical axis, and by the horizontal axis speed is denoted. So you will get a curve almost like this. Say this is the origin, x-axis, and this is the positive direction of x-axis. So first you will see that in the positive direction of x-axis, okay, starting from the origin, if you observe carefully the graph, okay, then you would see that in the positive direction of x-axis, the probability density increases. And what is represented by the vertical axis? It is probability density, and horizontal axis represents speed. So you will get the peak of the curve away from the origin, not near the origin but away from the origin. Okay, so you will get a curve like this. So at the middle, the length of the vertical axis, okay, that is the maximum, and that is, what is the meaning of that vertical line? The maximum height. The maximum height represents at that location the speed is maximum. So maximum speed is achieved for most of the particles. Means when probability density is the highest, there you are getting the maximum speed. And that region is very small for a given temperature. Means the region at which the speed becomes maximum is very small. That means in your given system, very few particles are moving with maximum speed. Okay, but if you increase the temperature of the system, in that case, what you would observe? So in that case, how you will compare? So in the same graph paper, you need to plot other curves also for other temperatures. That means you are in need for subplotting. So if you plot so many curves on the single graph paper, then you would see that the curve flattens out with increasing temperature. That means maximum speed achieved by the particles is going on increasing with increasing temperature. Okay, so this is the way any graph is studied. Okay. Anyway, mathematically many things are obtained using Maxwell-Boltzmann statistics. There are three speeds. One is called most probable speed, which is the maximum one. Most probable speed. Then comes the average speed. Average speed is nothing but the arithmetic average of the speed. If speeds are denoted by the speed of all the particles, say there are n number of particles and the speeds are denoted by v1, v2 up to vn, then arithmetic mean is what? It is v1 plus v2 up to vn and then divided by n. That is the arithmetic mean. You know this procedure. So this is the average speed. So you would find that always this maximum probable speed is more than the average speed. Then there is also root mean square velocity, which is equal to what? Mathematically this is equal to square of v1, means v1 square plus v2 square plus v3 square up to vn square. This way you add, then divide the summation by n, then again you take the under root, means square root of the result, then you would get RMS velocity, means root means square velocity. Okay, so again you find that this velocity, average velocity, is more than the RMS velocity. That means most probable velocity is more than the average velocity and average velocity is more than the RMS velocity. Okay, mathematical formula, you can see all these things on the screen. Okay, I am not going to show you the derivation of this Maxwell-Boltzmann distribution or Maxwell-Boltzmann statistics. So these are the conditions. Implications are many. Okay, in case of kinetic theory of gases, you can apply this Maxwell-Boltzmann statistics. In case of chemical reactions, to study chemical reactions, this law can be used, this statistics can be used. But for quantum systems, where quantum effects are important, means where quantum systems cannot, quantum effects cannot be neglected, in those cases you cannot use Maxwell-Boltzmann statistics. In that case, you must have to use either Fermi-Dirac statistics or Bose-Einstein statistics. To discuss all those things, I'll make separate videos, okay? Here in this video, I am discussing only about Maxwell-Boltzmann statistics. Yes, only for ideal gases, these statistics can be used. If in your given system, real gas is there, yes, everywhere real gas exists. Ideal gas is nowhere. Ideal gas is present nowhere. That means what? If in your system real gas is there, that means the interaction between the particles, if in your given system, interaction between the particles cannot be neglected. Because in the derivation of Maxwell-Boltzmann statistics, interaction between the particles are neglected. But if in your given system, interaction between the particles cannot be neglected, means the interactions are very important, then in that case you cannot use Maxwell-Boltzmann statistics. Yes, still if you want to use that Maxwell-Boltzmann statistics, in that case you need to take help of other mathematical models such as van der Waals equations. You know, van der Waals equations take care of the size of the particles, okay, as well as interaction, means collision between the particles. Those things are taken care of by van der Waals equation. There are so many equations, there are so many mathematical models. So you have to take help of all those equations, okay. All those means not at a time, any one of them which is suitable for your system, as well as Maxwell-Boltzmann statistics. Then only you can solve the problem which you are facing or you are interested to solve. Anyway, so this was all about Maxwell-Boltzmann statistics, okay. In my next videos you would see, means I would make my next videos on Fermi-Dirac statistics, then comes Bose-Einstein statistics, which are used for quantum systems. Anyway, so this is the end of this video. Thank you for watching this video.